The history of physics begins long before the word physics existed, long before formulas, laboratories, or scientific instruments. It begins with a simple, universal experience, humans observing the natural world and trying to make sense of it. Long before there were theories or equations, there were questions. Why does the sun rise and set? Why do objects fall? Why do seasons change? Why do some materials float while others sink? These questions were the seeds that eventually grew into the field we now call physics. In early human civilizations, the explanations for natural phenomena were not scientific but mythological. People attributed the movement of the heavens to gods, spirits, and supernatural forces. But even within these myths, there were patterns. Early civilizations noticed cycles and regularities. They saw that the sun moved predictably, that the phases of the moon followed a repeatable rhythm, and that the stars returned to the same positions each year. This recognition of patterns was the earliest step toward physics, because physics is, at its core, the study of patterns in nature. As society developed, curiosity became more organized. In ancient Egypt and Mesopotamia, people began using mathematics to track time, measure land, and predict astronomical events. Although their motivations were practical rather than scientific, these early observations laid important groundwork. Babylonian astronomers recorded star positions with surprising accuracy, not because they understood celestial mechanics, but because careful observation helped them manage calendars and agriculture. The Egyptians built monumental structures like the pyramids using geometric principles, even though they had no formal theory of mechanics. Their achievements demonstrated that practical physics existed long before theoretical physics. Physical knowledge was embedded in architecture, engineering, and daily life. Humans were experimenting with the laws of nature without yet realizing that these laws were universal. A major shift occurred in ancient Greece, where thinkers began to separate natural explanations from mythology. Instead of attributing lightning to gods, Greek philosophers asked whether nature could be explained by nature itself. Thales, often considered the first natural philosopher, proposed that natural phenomena had natural causes. This was a turning point because it established the idea that the universe followed rules, even if those rules were not yet discovered. Anaximander proposed that the Earth floated freely in space, while Pythagoras believed that mathematics revealed the structure of reality. Although these early ideas were often incorrect, they marked the first attempts to explain the world rationally. The Greeks also made significant contributions to understanding motion and matter. Democritus suggested that all matter was made of tiny, indivisible particles, which he called atoms. Remarkably, this idea would reappear in modern physics thousands of years later. Aristotle, although wrong about many things, dominated scientific thought for centuries. He believed that objects naturally sought their proper place, and that heavier objects fell faster than lighter ones. These ideas persisted because Aristotle created a comprehensive philosophical system that was appealing, even if it lacked experimental support. In this era, physics was not yet a science. It was an extension of philosophy. Despite their limitations, the Greeks advanced the study of physics in ways no previous civilization had. They attempted to explain the universe through reasoning, not myth. They developed geometry, optics, and early mechanics. They studied levers, pulleys, and buoyancy. Archimedes, one of the greatest minds of antiquity, discovered the principle of displacement, formulated laws of levers, and came close to inventing calculus. He demonstrated that natural phenomena could be described mathematically, hinting at the approach modern physics would eventually adopt. After the Greek era, scientific progress slowed due to political instability, wars, and the loss of knowledge. However, much of Greek science was preserved and expanded during the Islamic Golden Age. Scholars in the Middle East translated Greek, Persian, and Indian works, but they did far more than preserve them. They improved them through experimentation. During this period, physics began moving away from purely philosophical speculation and closer to an empirical discipline. Ibn al-Haytham, also known as Al-Hazen, formulated the earliest version of the scientific method. He insisted that theories must be tested through experiments, and that observation must override authority. His work in optics corrected Greek ideas, demonstrating that vision occurs when light reflects off objects and enters the eye, not by rays emitted from the eye. This shift toward experimental verification was crucial for the future of physics. In medieval Europe, progress was slower, but the foundation for modern physics continued developing. Universities emerged, and scholars began debating ideas about motion and natural laws. Thinkers such as Jean Buridan proposed the concept of impetus, a precursor to Newton's idea of inertia. These incremental advances refined humanity's understanding of motion, even if they did not yet form a coherent theory. Still, the greatest transformation was yet to come. The Renaissance reawakened interest in observation, measurement, and nature. Scientists and thinkers began challenging long-held assumptions. The invention of the printing press allowed knowledge to spread more efficiently than ever before. This era saw the rise of empirical science, science based on measurement rather than philosophy. Nicholas Copernicus proposed that the Earth orbited the Sun, not the other way around. This idea was revolutionary because it challenged centuries of belief rooted in Aristotelian cosmogony. Copernicus's work did not immediately change physics, but it reshaped humanity's understanding of its place in the universe. Galileo Galilei carried the momentum forward. He conducted experiments that directly contradicted Aristotle's theories. When he rolled balls down inclined planes, he discovered that objects accelerate at a constant rate regardless of their mass. He used telescopes to observe the phases of Venus, the moons of Jupiter, and the mountains on the moon, all of which supported the heliocentric model. Galileo emphasized experimentation, mathematics, and skepticism, key elements of modern physics. His work laid the foundation for the scientific revolution. The breakthrough moment in the history of physics came with Isaac Newton. Newton unified the heavens and the earth under the same set of laws. He introduced the three laws of motion, which describe how objects move in response to forces. He formulated the law of universal gravitation, demonstrating that the same force pulling an apple downward also governed the motion of planets. This was the first time anyone showed that the universe was governed by universal laws that applied everywhere. Newton also invented calculus, a mathematical tool essential for analyzing motion and change. For centuries, Newtonian physics defined humanity's understanding of the physical world, explaining motion, mechanics, heat, sound, and more. Newton brought structure and predictability to physics, transforming it into a truly scientific discipline. In the centuries after Newton, physics expanded rapidly. Scientists explored electricity, magnetism, heat, and optics. Experiments became more precise, and instruments became more advanced. Michael Faraday demonstrated that electricity and magnetism were connected, and James Clerk Maxwell unified these phenomena with a set of equations describing electromagnetic waves. These equations predicted that light itself was an electromagnetic wave, a groundbreaking discovery that linked optics to electromagnetism. The unification of electricity, magnetism, and light was one of the greatest achievements in classical physics and set the stage for the technologies that define modern society. As the 19th century progressed, physicists also studied heat and energy, leading to the development of thermodynamics. Researchers discovered the laws governing energy transfer, establishing that energy is conserved and that systems tend toward disorder. These principles became essential for understanding engines, chemistry, and statistical mechanics. Thermodynamics bridged the gap between microscopic particles and macroscopic phenomena. The concept of atoms also reemerged, supported by experimental evidence from chemistry and kinetic theory. By the late 19th century, physics appeared to be nearly complete. Some scientists even believed that all fundamental laws had been discovered. But nature had surprises waiting. By the early 20th century, classical physics encountered problems it could not solve. Experiments showed that light sometimes behaved like a particle, not a wave. Measurements of atomic spectra revealed energy levels that could not be explained with classical models. The behavior of electrons, radiation, and high-speed motion challenged established theories. These cracks in classical physics led to two revolutionary breakthroughs: relativity and quantum mechanics. Albert Einstein transformed physics with his theories of relativity. Special relativity showed that time and space are not absolute. It introduced the idea that time slows down and lengths contract at high speeds. It revealed the famous relationship E=mc², connecting mass and energy. General relativity went further, redefining gravity as the curvature of space-time caused by mass and energy. This theory accurately predicted phenomena such as the bending of light around stars and the expansion of the universe. Relativity reshaped cosmology, astrophysics, and our understanding of space and time. At the same time, quantum mechanics emerged to explain the behavior of particles on the smallest scales. Max Planck discovered that energy came in discrete packets. Niels Bohr proposed a model of the atom with quantized orbits. Werner Heisenberg developed matrix mechanics, while Erwin Schrödinger introduced wave mechanics. Quantum theory revealed that particles behave as both waves and particles, that outcomes are probabilistic, and that observation affects physical systems. This new field challenged intuition, philosophy, and classical assumptions. It also laid the groundwork for technologies such as transistors, lasers, and modern electronics. As quantum mechanics and relativity matured, physics continued advancing. Particle physics emerged, powered by accelerators that could probe deeper into the structure of matter. Scientists discovered quarks, leptons, bosons, and the forces governing their interactions. The Standard Model unified 3 of the 4 fundamental forces and successfully described the behavior of subatomic particles. Meanwhile, astrophysics expanded, uncovering black holes, neutron stars, and the cosmic microwave background radiation. These discoveries validated predictions of general relativity and shaped modern cosmology. Physics today stands at the intersection of immense complexity and deep simplicity. It seeks to unify quantum mechanics and gravity, explore dark matter and dark energy, understand the structure of space-time, and push the boundaries of computation and technology. From ancient observations of the stars to particle accelerators smashing atoms together at near-light speeds, the history of physics is a story of expanding curiosity, increasing precision, and a constant search for deeper truths about the universe. As physics entered the era shaped by Aristotle and the thinkers who followed him, ideas about motion and the structure of reality continued evolving through debates, refinements, and observations gathered from various cultures. Aristotle's work dominated not only Greece, but much of the Mediterranean and later the Islamic world, forming the backbone of natural philosophy for almost 2,000 years. His influence was so strong that even the errors within his framework became part of accepted scientific doctrine, repeated through generations. He believed that heavier objects fall faster than lighter ones, that motion requires a continuous force, and that the heavens operate under separate, perfect laws immune to the imperfections of Earth. His authority, symbolic and intellectual, created a foundation so stable that it discouraged challenges for centuries. It had also planted the seeds for one of the most important future transformations in human knowledge. To overthrow Aristotle's physics was not simply to correct a misconception. It was to reshape how we think, reason, and justify claims about the natural world. One of the most important contributions from the ancient era was the continuous curiosity about the nature of light. Empedocles had suggested that light traveled as some form of emission, while others believed the eye emitted rays to probe the world. The debates surrounding vision and optics may seem primitive today, but they introduced ideas that would later become essential for the scientific revolution. Greek and Hellenistic theories eventually mixed with the mathematical advancements nurtured in Alexandria, where scholars like Euclid wrote texts on optics using geometric reasoning. Their work was preserved and later expanded by scholars across continents and cultures, ultimately forming one of the bridges between ancient and early modern physics. While Greek influence spread westward through Rome, it dispersed eastward into regions where the Islamic Golden Age would emerge centuries later. This period played a crucial role in preserving, translating, and expanding ancient knowledge. In the 9th to 12th centuries, Baghdad became a global center of scientific inquiry where scholars like Al-Kindi, Al-Hazen, and Avicenna reshaped the foundations of physics. Al-Hazen, for example, produced groundbreaking research on optics, arguing that vision results from light entering the eye rather than rays leaving it. His method relied heavily on experimentation and observation, foreshadowing principles of the scientific method long before Europe embraced them. He studied the behavior of lenses, mirrors, refraction, and reflection with a precision that enabled future generations to refine optical theory. His work also challenged deeply rooted Greek assumptions and opened the door for new ways of thinking that emphasized proof over authority. Meanwhile, in medieval Europe, physics became intertwined with philosophy and theology as Aristotle's works were imported and integrated into scholastic teachings. Scholars like Thomas Aquinas and Roger Bacon attempted to reconcile classical thought with religious doctrine while also exploring natural principles. Although their inquiries did not generate modern physics, they questioned and analyzed inherited frameworks with growing attention to contradictions and gaps. By the time universities began forming across Europe, debates over natural philosophy were becoming increasingly rigorous, laying the intellectual groundwork for the seismic shift that would occur during the Renaissance and early modern period. By the 14th century, thinkers like Jean Buridan introduced new concepts that undermined core Aristotelian beliefs. Buridan's theory of impetus suggested that objects in motion possess an internal force that keeps them moving, which was an early precursor to the concept of inertia. Although his theory remained incomplete, it marked a turning point. The old notion that motion required constant force began to weaken, and the idea that objects maintain motion unless acted upon hinted at a future Newtonian framework. Other scholars, such as Nicole Oersma, used graphical methods to analyze motion, including concepts resembling velocity-time graphs centuries before analytic geometry or calculus. These intellectual steps, small but significant, signaled that classical ideas were beginning to crack. The Renaissance accelerated this change. Renewed interest in mathematics, art, engineering, and empirical observation created a culture in which the physical world was studied with new enthusiasm. Leonardo da Vinci explored mechanics, fluid dynamics, anatomy, and optics with extraordinary creativity. His notebooks reveal analyses of falling bodies, vortices in water, and the flight of birds, all demonstrating a mathematical curiosity about natural processes. Although many of his ideas were not published or widely known during his lifetime, his approach reflected a larger trend, an increasing willingness to observe nature directly rather than rely on inherited assumptions. As Europe transitioned into the 16th century, one figure emerged whose ideas would reshape not just physics, but humanity's understanding of its place in the universe: Nicholas Copernicus. When he proposed that Earth revolved around the sun rather than the other way around, he initiated a paradigm shift. This was not physics in a modern sense, but it altered the cosmic framework that physics operated within. A sun-centered universe presented the possibility that motion could be simpler and more elegant than the complex astronomical models that had persisted for centuries. Although Copernicus relied heavily on philosophical reasoning rather than empirical proof, his work invited others to investigate the laws governing celestial and terrestrial motion under unified principles. The next major breakthrough came from Johannes Kepler, who combined meticulous astronomical observations with mathematics to derive 3 laws describing planetary motion. Kepler demonstrated that planets do not move in perfect circles but in ellipses, that they sweep out equal areas in equal times, and that their orbital periods relate systematically to their distances from the Sun. These discoveries signaled the beginning of a physics rooted in precise measurement and mathematical patterns. Kepler's laws created testable predictions and established that celestial bodies followed quantifiable rules, a dramatic departure from the idea of divine or perfect motion. In Italy, a contemporary of Kepler was dismantling other long-held assumptions. Galileo Galilei, often considered one of the founders of modern physics, questioned Aristotle's claims about falling bodies in motion. Using inclined planes and careful timing, Galileo discovered that objects accelerate uniformly under gravity regardless of their mass. His insistence on repeatable experiments and mathematical descriptions of nature formed the basis of scientific methodology. Galileo also used telescopes to observe features on the moon, moons orbiting Jupiter, and phases of Venus, evidence that challenged the Aristotelian worldview and supported heliocentrism. Even his studies on projectile motion showed that parabolic trajectories could be explained mathematically, unifying celestial and terrestrial mechanics in a way that had never been attempted before. While Galileo revolutionized motion, another thinker would soon synthesize centuries of ideas into a single framework. Isaac Newton, building upon Galileo's kinematics and Kepler's planetary laws, formulated 3 laws of motion that became the foundation of classical mechanics. His first law formalized inertia. His second established the relationship between force, mass, and acceleration. His third introduced action and reaction. Newton also developed the law of universal gravitation, demonstrating that the same force causing apples to fall also controls the motion of planets. This unification of heaven and earth under a single mathematical law marked one of the greatest achievements in human intellectual history. Newton's Principia Mathematica laid the foundation for an entire era of scientific progress. His calculus, though independently developed by Leibniz in parallel, gave future scientists the mathematical tools needed to describe change, motion, and the continuous nature of natural processes. For centuries, the Newtonian framework successfully explained everything from pendulums to tides to planetary orbits. It was so effective that many believed physics was complete, with only minor details left to refine. However, as the world moved into the 18th and 19th centuries, cracks quietly began to appear, cracks that would eventually reshape physics once again. The rise of thermodynamics introduced new challenges. Early experiments on heat, engines, and energy revealed that mechanical work, temperature, and internal energy were deeply interconnected. Scientists like Sadi Carnot, Rudolf Clausius, and James Clerk Maxwell discovered laws governing entropy, efficiency, and the statistical nature of particles. Their insights provided a clearer understanding of heat as a form of energy transfer rather than a material substance. The concept of energy itself, once vague and underdefined, became central to physics. Simultaneously, the study of electricity and magnetism underwent a transformation. Experiments by Michael Faraday revealed unexpected links between electric currents and magnetic fields. Faraday's work inspired James Clerk Maxwell to unify electricity, magnetism, and light within a set of equations that became the foundation of electromagnetic theory. Maxwell showed that light itself is an electromagnetic wave, a discovery that expanded the reach of physics across the electromagnetic spectrum and paved the way for modern communication technologies. As the 19th century closed, physics stood at a remarkable frontier. Classical mechanics, thermodynamics, and electromagnetism formed a powerful framework that explained an enormous range of phenomena. Yet certain anomalies, such as the behavior of blackbody radiation, the properties of electrons, and the constancy of the speed of light, revealed that the classical worldview was incomplete. These unresolved puzzles would soon lead to the 2 monumental revolutions of 20th century physics: relativity and quantum mechanics. As the 19th century approached its final decades, physicists believed they had nearly completed the understanding of nature. The laws of motion, the behavior of heat, the nature of electricity and magnetism, and the mathematical structure that connected all of these seemed to leave little room for major surprises. Many scientists even openly declared that the age of great discoveries had ended, and that physics was reduced to refining the remaining decimal places of known constants. Yet it was precisely during this period of confidence that the universe quietly began signaling that classical physics, despite its immense successes, was fundamentally incomplete. These signals appeared as small inconsistencies, tiny cracks in an otherwise solid wall, but they were enough to hint that a profound transformation was coming. One of the first cracks emerged from the study of blackbody radiation. A blackbody is an idealized object that perfectly absorbs all radiation falling upon it and emits radiation according to its temperature. When experimentalists attempted to measure the distribution of light such an object emits, their data did not match predictions from classical theories. As the wavelength decreased, classical physics predicted an infinite amount of energy, a catastrophic divergence known as the ultraviolet catastrophe. No physical system, let alone the universe itself, could behave in that impossible way. Yet experiments showed a clear pattern that classical equations simply could not reproduce. For years, the mismatch stood as an unresolved contradiction, one that would eventually force the revision of physics from its foundations. Another inconsistency was hidden in the behavior of light and the structure of the ether, the hypothetical medium through which light waves were believed to travel. Maxwell's equations suggested that the speed of light should be constant, independent of the motion of the observer or the source. But this clashed with the principle of relative motion inherited from Newtonian mechanics. If the ether existed, Earth's motion through it should create detectable variations in the speed of light as the planet orbited the sun. The Michelson-Morley experiment, designed to measure these variations, consistently failed to detect any difference, implying that the ether might not exist at all. This was troubling because classical physics had no alternative explanation for how waves could propagate through empty space. Light behaved like a wave, but a wave with no medium defied the classical worldview. The structure of the atom also presented mysteries. Experiments such as those by J. Thomson revealed the existence of electrons, tiny negatively charged particles far smaller than any known entity. If atoms contain these particles, then classical electromagnetism predicted that electrons orbiting a nucleus would radiate energy continuously and rapidly spiral inward, causing atoms to collapse. Yet atoms were undeniably stable. Something was missing, something classical physics could not describe. It was in this context of confusion and contradiction that Max Planck stepped forward with a bold idea. In 1900, he proposed that energy is not exchanged continuously, but in discrete packets he called quanta. This suggestion, originally made as a mathematical trick to fix the blackbody radiation problem, implied that nature might operate in fundamentally discontinuous ways. Although Planck himself was reluctant to embrace the implications, his idea planted the seed for quantum theory. The next major leap came from a young patent clerk in Switzerland named Albert Einstein. In 1905, a year now known as his Annus Mirabilis, Einstein published a series of papers that reshaped physics. To explain the photoelectric effect, the observation that light ejects electrons from metal surfaces in ways classical wave theory could not predict, Einstein suggested that light itself behaves as a collection of discrete particles, later called photons. This radical proposal extended Planck's quantization into the heart of electromagnetic theory, revealing a dual nature of light that combined both wave and particle characteristics. This idea was deeply unsettling to classical physicists, but it successfully explained experimental results that had defied understanding. In the same year, Einstein tackled the strange constancy of the speed of light by proposing the special theory of relativity. He discarded the ether entirely and redefined the concepts of space and time. According to special relativity, the laws of physics are the same in all inertial frames, and the speed of light is a universal constant, not dependent on the motion of the observer. This required a dramatic revision to our understanding of time, introducing the ideas that time dilates, lengths contract, and simultaneity is relative. Suddenly, time was not absolute, but intertwined with space in a four-dimensional continuum later called spacetime. Einstein's work did not stop there. A decade later, he developed the general theory of relativity, an even more profound transformation of physics. General relativity presented gravity not as a force between masses, as Newton had described, but as a curvature of space-time caused by mass and energy. Objects in free fall follow the straightest possible paths through curved space-time, creating the appearance of gravitational attraction. This theory elegantly explained anomalies, such as the precession of Mercury's orbit, and predicted phenomena like gravitational lensing, which would be confirmed many decades later. General relativity expanded physics beyond the Newtonian universe into a realm where space could stretch, bend, and even rip apart. While relativity revolutionized the large-scale picture of the universe, quantum mechanics began reshaping the microscopic world. Niels Bohr introduced a model of the hydrogen atom in which electrons occupy quantized orbits, explaining spectral lines that had puzzled scientists for years. Louis de Broglie proposed that particles such as electrons possess wave-like properties, establishing the concept of matter waves. These ideas culminated in the development of wave mechanics by Owen Schrödinger and matrix mechanics by Werner Heisenberg. Schrödinger's wave equation described how quantum states evolve, while Heisenberg formulated the uncertainty principle, showing that certain pairs of quantities, such as position and momentum, cannot be measured simultaneously with arbitrary precision. Quantum mechanics differed from classical physics not just in detail, but in structure, philosophy, and interpretation. Classical physics had portrayed the universe as predictable, deterministic, and governed by continuous laws. Quantum mechanics introduced probabilistic outcomes, wave, particle duality, and a fundamentally statistical description of nature. Events did not occur with certainty, but according to probabilities derived from wave functions. This shift was not merely a refinement of old ideas, it was a new way of thinking about nature. As quantum theory developed further, Paul Dirac unified quantum mechanics with special relativity, predicting the existence of antimatter, particles identical to ordinary matter but with opposite charge. His prediction seemed astonishingly speculative until the discovery of the positron by Carl Anderson provided direct experimental confirmation. Quantum electrodynamics, developed later by Richard Feynman, Julian Schwinger, and Sunitaro Tominaga, became one of the most precise and successful theories in the history of science, describing how particles interact through the electromagnetic force with extraordinary accuracy. Meanwhile, discoveries in nuclear physics revealed an inner complexity previously unimaginable. Ernest Rutherford's experiments showed that most of an atom's mass resides in a tiny, dense nucleus. This nucleus contained protons and, as James Chadwick later discovered, neutrons. Understanding the forces that held nuclei together became a major challenge, leading to the development of quantum chromodynamics and the modern theory of the strong nuclear force. Nuclear physics also led to applications that would change human history, both in the form of nuclear energy and devastating weapons. The 20th century eventually saw the emergence of the standard model of particle physics, which categorized fundamental particles into quarks, leptons, and gauge bosons. This model unified electromagnetic, weak, and strong interactions under a comprehensive theoretical framework, though gravity remained outside its scope. High-energy particle accelerators allowed scientists to probe deeper into matter, revealing a zoo of particles and confirming predictions such as the W and Z bosons, gluons, and finally the Higgs boson in 2012. While these advances explained much of nature's behavior, they also revealed new mysteries. Dark matter, dark energy, neutrino oscillations, and the apparent incompleteness of both quantum mechanics and general relativity set the stage for the next era of physics, one still unfolding today. Understanding these mysteries requires technologies and mathematical tools beyond anything in the early days of physics. But the underlying human curiosity that drives progress remains unchanged. As the 20th century advanced, physics split into two monumental pillars: quantum mechanics, which governed the microscopic world of atoms and subatomic particles, and general relativity, which described the gravitational behavior of massive bodies and the structure of space-time itself. Both theories were remarkably successful within their domains, yet they refused to merge into a single unified framework. This incompatibility became one of the defining challenges of modern physics. Still, even without unification, each field expanded dramatically, revealing new layers of complexity in both the extremely small and the extremely large. On the quantum side, experimental discoveries multiplied rapidly. The invention of particle accelerators allowed scientists to recreate the conditions present just moments after the Big Bang. By smashing particles together at high energies, researchers uncovered a growing list of components that made up the atom. Early discoveries such as pions and muons suggested that the simple proton-electron model was only the beginning. As accelerators grew more powerful, so did the complexity of particle interactions. What initially appeared to be a chaotic zoo of particles eventually revealed a pattern. Physicists realized that many of the newly discovered particles were not fundamental, but composed of even smaller building blocks called quarks. Quarks came in flavors such as up, down, strange, charm, bottom, and top. These quarks interacted through the strong nuclear force, mediated by particles known as gluons. This framework became the foundation for quantum chromodynamics, a key component of the Standard Model. The Standard Model successfully unified three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Electromagnetism was described through quantum electrodynamics, the weak force through the electroweak theory developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg, and the strong force through quantum chromodynamics. Together, these theories created a highly predictive framework that matched experimental data with extraordinary accuracy. Yet despite its success, the Standard Model was clearly incomplete. It did not explain gravity, it did not account for dark matter or dark energy, and it treated neutrinos as massless despite growing evidence that they possess tiny but non-zero masses. Meanwhile, general relativity opened the door to understanding the structure and evolution of the universe as a whole. Einstein's equations predicted that the universe could not remain static. It must either expand or contract. At first, Einstein believed this prediction was a mistake, and he introduced a cosmological constant to force a stable universe. However, observations by Edwin Hubble in 1929 demonstrated that distant galaxies were receding from us, implying that the universe was indeed expanding. This discovery transformed cosmology into a quantitative science. Later observations revealed that not only is the universe expanding, but the expansion is accelerating. This phenomenon was attributed to a mysterious form of energy pervading space, known as dark energy. Astrophysics progressed in parallel with particle physics, creating a fascinating interplay between the largest and smallest scales of reality. For example, understanding nuclear fusion helped explain how stars produce energy. The same quantum processes that govern the interactions of particles inside atoms also determine the behavior of dense stellar objects, such as neutron stars and white dwarfs. The life cycle of stars, from formation to fusion to collapse, relied heavily on the physics of quantum interactions, nuclear forces, and gravitational dynamics. The explosive deaths of massive stars, supernovae, seeded the universe with heavy elements forged through nuclear reactions, laying the foundation for planets and life. Black holes emerged as some of the most extraordinary objects predicted by general relativity. Initially considered mathematical curiosities, black holes became mainstream scientific objects after increasing evidence showed that extremely dense stellar remnants could collapse into regions where gravity was so intense that not even light could escape. The discovery of Cygnus X-1, one of the first strong black hole candidates, transformed black holes from theory to observation. Over time, astronomers detected supermassive black holes residing at the centers of galaxies, including the Milky Way. These gargantuan objects, millions or billions of times more massive than the Sun, became crucial drivers of galaxy evolution, feeding on surrounding matter and releasing immense amounts of radiation in the process. Quantum mechanics also extended into fields such as condensed matter physics, where the behavior of electrons in solids revealed phenomena like superconductivity and superfluidity. These discoveries had profound technological implications. The development of semiconductors, for instance, led directly to the creation of transistors and integrated circuits, which revolutionized computing and communications. Quantum mechanics did not merely reshape theoretical understanding. It became the backbone of the modern technological world. In the late 20th century, high-energy physics continued to push boundaries. Experiments at major research facilities such as Fermilab and CERN explored the behavior of particles at increasingly high energies. The large accelerators allowed physicists to probe conditions similar to those moments after the Big Bang, testing the predictions of the Standard Model with precision. These experiments confirmed the existence of the W and Z bosons, crucial to the electroweak force, and later provided one of the most sought-after discoveries in particle physics, the Higgs boson. Proposed by Peter Higgs and others, the Higgs field explained why fundamental particles have mass. Detecting the Higgs boson at the Large Hadron Collider in 2012 was a monumental validation of the Standard Model, yet it also emphasized the gaps in our understanding. Even with the Higgs accounted for, many fundamental questions remained unanswered. One of the most significant mysteries involved the composition of the universe. Observational evidence revealed that ordinary matter, the stuff made of atoms, constitutes only a small fraction of cosmic matter. The motions of galaxies and clusters suggested the presence of invisible mass, now called dark matter. Despite overwhelming gravitational evidence, dark matter has not been directly detected, and its nature remains one of the largest open questions in physics. Similarly, dark energy, responsible for the accelerating expansion of the universe, constitutes an even larger fraction of the universe's energy content, yet it remains poorly understood. Efforts to unify quantum mechanics and general relativity produced ambitious theories, including string theory and loop quantum gravity. String theory proposed that fundamental particles are tiny vibrating strings, while loop quantum gravity attempted to quantize spacetime itself. Both frameworks offered elegant mathematical structures, but neither has yet achieved experimental confirmation. The challenge of reconciling gravity with quantum mechanics remains one of the most profound scientific quests of the modern age. At smaller scales, experiments with quantum entanglement and quantum information revealed properties of nature that defy classical intuition. The realization that particles can exhibit instantaneous correlations across vast distances inspired new fields such as quantum computing and quantum cryptography. Quantum computers, still in early stages, promise to solve certain classes of problems far beyond the capabilities of classical machines. These advancements highlight how the abstract world of quantum theory could shape future technology just as dramatically as it shaped the modern world. The 21st century has brought unprecedented growth in observational and experimental tools. Telescopes have become more sensitive, capturing light across the electromagnetic spectrum and even detecting gravitational waves. The first observation of gravitational waves by the LIGO detectors in 2015 confirmed a major prediction of general relativity and opened a new era of astronomy. These waves, produced by massive events such as black hole mergers, allow scientists to study the universe using not only light, but the vibrations of space-time itself. At the same time, advances in precision experiments continue to test the Standard Model for signs of new physics. Measurements of particle magnetic moments, decay rates, and rare interactions may reveal deviations hinting at phenomena not yet understood. Even the search for dark matter has diversified, with experiments probing everything from weakly interacting particles to ultralight fields. The next breakthrough could emerge from any of these directions, potentially reshaping the foundations of physics once again. The ongoing exploration of physics has always been driven by the same questions that inspired early humans. What is the universe made of? How does it work? And what are the fundamental rules governing its behavior? From ancient observations of falling objects to the study of black holes and quantum particles, physics has expanded in scope, precision, and ambition. Each century has added new layers of understanding, revealing that the universe is far stranger and more intricate than previously imagined. Yet throughout this history, certain principles remain consistent. Observation, measurement, mathematics, and critical reasoning continue to guide the investigation of nature, ensuring that scientific inquiry evolves while remaining grounded in evidence. The interplay between theory and experiment is central to this evolution. In many cases, theoretical predictions precede experimental confirmation by decades or even centuries. Einstein's general relativity, for example, predicted gravitational waves long before LIGO detected them. Similarly, Dirac's prediction of antimatter preceded the experimental discovery of the positron. These examples illustrate a recurring theme in physics. Human imagination, guided by rigorous mathematics, often glimpses phenomena long before instruments can observe them. The predictive power of physics is one of its most remarkable features, allowing scientists to anticipate the behavior of systems across vast scales, from subatomic particles to the expansion of the universe itself. Another recurring pattern is the unexpected unity of nature. Early humans distinguished between phenomena on Earth and in the heavens, treating them as governed by separate rules. Ancient and medieval frameworks perpetuated this divide. Newton's unification of terrestrial and celestial mechanics was a turning point, showing that the same laws apply everywhere. Later unifications, such as Maxwell's equations, revealed that seemingly distinct phenomena, electricity, magnetism, and light, were aspects of a single underlying reality. Quantum mechanics, too, demonstrated that microscopic particles and macroscopic materials are governed by the same fundamental principles, even when behavior appears counterintuitive. This quest for unification drives much of modern theoretical physics, including efforts to reconcile gravity with quantum mechanics, understand dark energy, and explore the possible multidimensional structure of the universe. The technological consequences of these discoveries are profound. The theoretical insights of the past century have generated applications unimaginable to Newton, Galileo, or even Faraday. Electronics, semiconductors, lasers, medical imaging, GPS, nuclear power, and quantum computing all rely on principles developed through fundamental physics. What began as human curiosity about falling objects, planetary motion, and light has evolved into a toolkit that reshapes society, medicine, communication, and industry. In a sense, the practical impact of physics is inseparable from its intellectual journey. The drive to understand nature inevitably produces tools that transform human civilization. Physics has also challenged the philosophical and conceptual understanding of reality. Relativity taught that space and time are not absolute. Quantum mechanics revealed that measurement itself affects the systems being observed. The probabilistic nature of quantum events and the entanglement of particles force us to reconsider assumptions about determinism, causality, and locality. Even in the realm of classical physics, concepts such as energy conservation, symmetry, and invariance carry deep implications beyond mere calculation. The study of physics is not simply about describing what happens, but also about understanding the fundamental nature of existence itself. Throughout its history, physics has been shaped by collaboration, debate, and the exchange of ideas across cultures. Greek philosophers laid the foundations. Islamic scholars preserved and extended this knowledge. European thinkers synthesized observation, mathematics, and experimentation. Modern physicists from around the globe continue to push the boundaries. The history of physics is thus not only a chronicle of ideas, but also a story of human ingenuity, curiosity, and cooperation. Scientific progress rarely occurs in isolation. Discoveries often build on centuries of accumulated knowledge, debate, and refinement. Looking forward, the frontiers of physics are both daunting and exhilarating. Understanding dark matter, dark energy, and the unification of forces could redefine our comprehension of the universe. Quantum technologies promise to revolutionize computation, communication, and encryption. Gravitational wave astronomy and high-precision cosmology allow us to observe phenomena billions of light years away and moments after the Big Bang. Particle physics continues to explore the building blocks of matter at ever higher energies. Each step forward brings the potential for surprises that could challenge existing theories, just as quantum mechanics and relativity did in the 20th century. The history of physics, therefore, is far from complete. It is an ongoing journey of discovery and understanding. The story of physics demonstrates that curiosity, observation, and systematic inquiry are humanity's most powerful tools. By asking fundamental questions, testing ideas, and rigorously analyzing the results, humans have uncovered principles that explain motion, energy, light, matter, and the fabric of space-time. From simple experiments with rolling balls and falling apples to the observation of gravitational waves and quantum entanglement, the trajectory of physics is a testament to the human capacity for knowledge. It shows that while the universe may be vast, complex, and at times counterintuitive, it is intelligible through reason, measurement, and imagination. Finally, the history of physics is a story of continuity and change. While the methods, instruments, and scope of study have evolved dramatically, the underlying drive to understand the universe remains unchanged. Each generation of scientists stands on the shoulders of those who came before, adding clarity, insight, and precision to the shared enterprise of knowledge. As physics progresses, it not only illuminates the workings of the natural world, but also expands humanity's sense of possibility, creativity, and understanding. The journey that began with the earliest observations of nature continues today, promising discoveries that are as profound and transformative as those that define the past. In the 21st century, physics continues to confront both experimental and theoretical frontiers. The universe appears stranger and more complex than even Einstein or Bohr could have imagined. Observations from telescopes and satellites reveal a cosmos dominated by invisible components, dark matter, and dark energy. Galaxies rotate in ways that cannot be explained by visible matter alone, suggesting that the majority of matter in the universe is not directly observable. Dark energy, first detected through the accelerating expansion of the universe, makes up roughly 70% of the universe's energy content. These discoveries challenge our deepest assumptions, indicating that most of the cosmos operates in ways still beyond human comprehension. Understanding these phenomena requires not just incremental advances, but potentially radical reconceptualization of physics. The search for a theory of everything, an elegant framework uniting general relativity and quantum mechanics, has become a central goal of modern theoretical physics. Gravity, described exquisitely by relativity, resists incorporation into the quantum framework that governs subatomic particles. String theory offers one possible solution, suggesting that fundamental particles are not points but tiny vibrating strings, with different vibration modes corresponding to different particles. String theory implies the existence of extra spatial dimensions beyond the familiar three, hinting at a universe far more intricate than everyday perception reveals. Yet, despite decades of work, these ideas remain largely speculative, lacking direct experimental verification. Alternative approaches, such as loop quantum gravity, attempt to quantize space-time itself, proposing that space and time are not continuous but composed of discrete units. These theories, though mathematically sophisticated, remain on the frontier between known physics and imagination. Meanwhile, quantum mechanics continues to astonish with its paradoxes and applications. Quantum entanglement, famously described by Einstein as spooky action at a distance, shows that particles can exhibit correlations across vast distances instantaneously. Quantum teleportation experiments have confirmed these correlations, opening the door to revolutionary technologies in computing, cryptography, and secure communication. Quantum computers, still in their infancy, harness superposition and entanglement to perform calculations that would be impossible for classical machines. The theoretical understanding developed by Schrödinger, Heisenberg, and others now fuels the development of practical technologies that may redefine computation, material science, and information processing. Cosmology, too, has reached unprecedented precision. Observations of the cosmic microwave background, the afterglow of the Big Bang, allow scientists to reconstruct the early universe with astonishing detail. Measurements of galaxy distributions, gravitational lensing, and supernovae inform models of cosmic evolution, helping physicists estimate the age, composition, and expansion history of the cosmos. Large-scale collaborations, such as the Planck satellite and the Hubble Space Telescope, have provided data of extraordinary clarity, enabling a synthesis of theory and observation that was unimaginable even a century ago. These tools allow humans not only to understand the universe on its grandest scale, but also to test fundamental physics in extreme conditions far beyond any laboratory on Earth. The study of extreme astrophysical phenomena continues to yield surprises. Neutron stars, black holes, and supernovae test the limits of physics under conditions of density, temperature, and energy unattainable on Earth. Observations of gravitational waves, first confirmed in 2015, provide a new window into these violent events, allowing scientists to study the collision of black holes and neutron stars in real time. This emerging field, gravitational wave astronomy, exemplifies how modern physics integrates classical and quantum understanding with technological innovation to explore previously inaccessible phenomena. Each discovery challenges assumptions, refines models, and sometimes overturns long-held beliefs. At the smallest scales, particle physics presses forward with experiments at facilities such as the Large Hadron Collider. Beyond confirming the Higgs boson, physicists now search for signals of supersymmetry, extra dimensions, or new particles that might explain dark matter. These efforts demand collaboration on a global scale, with thousands of scientists working together to design experiments, analyze vast datasets, and interpret results. The pace of discovery is accelerating, but the universe continues to surprise, reminding physicists that even the most elegant theories may be incomplete or provisional. The history of physics, viewed in its entirety, demonstrates the iterative nature of scientific knowledge. Early humans began with observation and curiosity, recording patterns and seeking explanations. Ancient Greeks, Islamic scholars, Renaissance thinkers, and modern physicists each contributed layers of understanding, building upon prior work while challenging assumptions. Breakthroughs emerged not just from isolated genius, but from collective effort, rigorous testing, and a willingness to question established ideas. Newton unified motion and gravitation. Maxwell revealed the electromagnetic foundations of light. Einstein reconceptualized space and time, and quantum mechanics unveiled a probabilistic, interconnected microscopic reality. Each advance pushed the boundaries of human comprehension, illustrating both the power and the limitations of scientific inquiry. Physics has also become increasingly interdisciplinary, connecting with chemistry, biology, material science, and engineering. The same principles that describe subatomic particles also govern chemical reactions, electronic devices, and biological processes. Techniques developed in physics, such as spectroscopy, imaging, and computational modeling, have transformed medicine, energy, technology, and industry. The intellectual legacy of physics extends far beyond academic inquiry. It shapes the world in profound and tangible ways. From harnessing electricity to exploring outer space, the study of physical laws underpins nearly every aspect of modern life. As we contemplate the future, the challenges of physics remain as daunting as they are inspiring. Understanding dark energy, unifying gravity with quantum mechanics, probing the structure of space-time, and unraveling the ultimate nature of matter and energy will likely occupy generations of scientists. Yet history demonstrates that the pursuit of knowledge is cumulative and transformative. The methods and principles established over millennia observation, measurement, experimentation, mathematical reasoning, and critical analysis continue to guide discovery. Each era builds upon the last, showing that human curiosity and ingenuity are the constants driving progress. Ultimately, the history of physics is a story of exploration, creativity, and the relentless quest to understand the universe. It illustrates that while nature is complex, it is not incomprehensible. Human beings, equipped with curiosity, intelligence, and perseverance, can gradually uncover the principles governing reality, even when those principles defy intuition. The narrative of physics, stretching from the first observations of falling objects to the study of black holes, quantum entanglement, and the cosmic frontier, reflects a universal theme: the unyielding human drive to understand, explain, and harness the forces that shape existence. The journey continues. Physics, far from complete, faces profound mysteries and tantalizing possibilities. New technologies, experimental methods, and theoretical frameworks promise to reveal truths that might redefine our understanding of the universe, just as Einstein, Planck, Bohr, and Newton redefined it in their time. The pursuit of physics remains a testament to human curiosity, creativity, and persistence, demonstrating that even the vast, complex, and mysterious cosmos can, in principle, be explored, understood, and appreciated. The story is ongoing, and each generation contributes to a narrative that spans thousands of years, connecting past inquiry with the infinite possibilities of the future. As physics progresses deeper into the 21st century, the frontiers of research increasingly blend the boundaries between the observable and the speculative. Scientists now explore realms that were once considered purely theoretical or even philosophical. Concepts like multiverses, extra dimensions, and the fundamental fabric of space-time challenge not only classical intuition, but also the way humans think about reality itself. These speculative frameworks, while not yet confirmed experimentally, are grounded in rigorous mathematics and attempt to reconcile the gaps left by existing theories. For instance, string theory suggests that all particles and forces may arise from tiny, vibrating strings existing in multiple dimensions beyond the familiar three. If proven, this would unify gravity with quantum mechanics, creating a long-sought theory of everything that connects the largest scales of the cosmos with the smallest components of matter. The exploration of extreme environments, both terrestrial and cosmic, continues to drive experimental innovation. Particle accelerators such as the Large Hadron Collider allow physicists to probe energy scales previously inaccessible, recreating conditions similar to those immediately following the Big Bang. These experiments not only test existing theories, but also search for new particles, symmetries, and interactions that might illuminate the nature of dark matter and other unresolved phenomena. Meanwhile, space-based observatories monitor the cosmos across the entire electromagnetic spectrum, capturing signals from distant galaxies, black holes, and cosmic background radiation. Observations of phenomena like gravitational waves, detected from colliding black holes and neutron stars, provide a new lens through which to study the universe, complementing traditional light-based astronomy and revealing the dynamic nature of space-time itself. Quantum information science represents another frontier where physics merges with technological application. Quantum computing, which exploits superposition and entanglement, promises to revolutionize computing by solving problems that are intractable for classical machines. Quantum cryptography leverages the inherent uncertainty and correlation of quantum states to create secure communication channels, theoretically impervious to eavesdropping. These applications exemplify how abstract principles discovered over a century ago now form the foundation of potentially transformative technologies. They also highlight a recurring theme in physics: that deep understanding of nature often precedes its practical application, sometimes by decades or centuries. Simultaneously, physicists are increasingly turning their attention to understanding the emergent properties of complex systems. From condensed matter physics to cosmology, Researchers study how large-scale behavior arises from interactions between simple components. Superconductivity, superfluidity, and topological phases of matter reveal properties that cannot be deduced by studying individual particles alone, illustrating that collective behavior introduces entirely new phenomena. Similarly, in cosmology, the large-scale structure of the universe emerges from the interactions of dark matter, dark energy, and ordinary matter over billions of years. These studies emphasize that physics is not merely a catalog of particles or forces, but a framework for understanding systems at all scales, from quarks to galaxies. The integration of computation and simulation has become essential to modern physics. Complex systems that cannot be solved analytically are now explored using sophisticated numerical models and high-performance computing. Simulations of galaxy formation, black hole mergers, plasma dynamics, and climate systems allow scientists to test hypotheses and predict outcomes in ways that experiments alone cannot achieve. Computational physics acts as a bridge between theory and observation, enabling exploration of regimes that are either too large, too small, or too extreme for direct experimentation. The marriage of theory, computation, and observation demonstrates the evolving methodology of physics and the increasing sophistication of the tools used to explore nature. Collaborative efforts in global physics projects illustrate the scale and ambition of modern scientific inquiry. International collaborations, such as the Large Hadron Collider, the Event Horizon Telescope, and gravitational wave observatories like LIGO and Virgo exemplify the collective effort required to tackle the most profound questions in physics. Thousands of scientists from dozens of countries coordinate to design, build, and operate experiments, analyze enormous datasets, and interpret results. This global approach ensures that progress is both rapid and robust, and it highlights the inherently collaborative nature of scientific discovery. The pace of discovery has accelerated, yet the universe continues to surprise, reminding us that the frontiers of knowledge are vast and often unpredictable. Despite the progress, fundamental questions remain unresolved. The true nature of dark matter and dark energy, the unification of gravity with quantum mechanics, the origins of the universe, and the ultimate fate of space-time itself remain subjects of intense investigation. These mysteries illustrate that physics, even after thousands of years of inquiry, is far from complete. Each discovery answers some questions while raising new ones, creating a dynamic cycle of investigation and refinement. This iterative process is the hallmark of science. Knowledge grows through observation, theory, experimentation, and the willingness to question assumptions. The journey of physics also reflects a broader human endeavor, the desire to understand reality, to predict phenomena, and to harness knowledge for practical purposes. From the earliest observations of the stars and falling objects to the exploration of quantum states and the structure of space-time, physics represents a continuum of curiosity and discovery. It shows how human ingenuity, systematic reasoning, and persistent inquiry can gradually unveil the workings of a universe that is vast, complex, and often counterintuitive. Each generation contributes to this legacy, building on the foundations laid by predecessors and expanding the boundaries of understanding. Ultimately, the history of physics is a story of exploration, creativity, and the relentless pursuit of knowledge. It demonstrates that, while nature is complex, it is not beyond human comprehension. The laws and principles uncovered through centuries of study reveal patterns and connections that allow humans to interpret, predict, and influence the world. The narrative of physics, from ancient observations to modern frontiers, embodies the extraordinary capacity of humans to understand the universe, and it serves as a reminder that the pursuit of knowledge is a journey without end. The questions of today about dark matter, quantum gravity, multiverses, and the limits of computation will define the discoveries of tomorrow, continuing a story that began with simple curiosity and will likely extend far beyond our current imagination. The 21st century has opened a new chapter in the exploration of physics, a chapter where imagination and experimentation push the boundaries of what was once thought possible. Emerging fields such as quantum information, gravitational wave astronomy, and high-energy particle physics are not only redefining our understanding of the universe, but also hinting at entirely new realms of reality. The lines between what is observable and what is theoretical blur, demanding that physicists adopt ever more sophisticated mathematical frameworks to describe phenomena far beyond everyday experience. This era exemplifies the dual nature of modern physics. It is simultaneously experimental, grounded in data, and profoundly speculative, inviting bold conceptual leaps that may eventually reshape our understanding of existence itself. One of the most remarkable developments is in quantum information science, where principles first uncovered in the early 20th century are being harnessed for revolutionary technologies. Quantum entanglement, once considered an oddity of theory, now enables secure communication channels that are fundamentally impervious to eavesdropping. Quantum computing, which leverages superposition to perform calculations on vast numbers of possibilities simultaneously, promises to tackle problems that classical computers could never solve. Material scientists are exploring quantum effects in novel systems, such as topological insulators and superconductors, which could lead to unprecedented advancements in electronics, energy efficiency, and information storage. These applications demonstrate that the abstract discoveries of the past century are not merely intellectual achievements. They form the foundation of a technological transformation that is unfolding before our eyes. In parallel, gravitational wave astronomy has opened an entirely new way to perceive the universe. Traditionally, humans have observed the cosmos through electromagnetic signals, visible light, radio waves, X-rays, and gamma rays. The detection of gravitational waves, however, allows scientists to hear the vibrations of space-time itself, emitted by the most violent events in the universe, such as black hole collisions and neutron star mergers. This development has not only confirmed Einstein's predictions, but also provided a unique observational tool to explore phenomena that were previously inaccessible. The ability to study these cosmic events in multiple ways, both through light and gravitational waves, has inaugurated an era of multi-messenger astronomy, where complementary forms of data combine to create a richer understanding of the universe. Meanwhile, particle physics continues its relentless quest to uncover the fundamental building blocks of reality. Beyond confirming the existence of the Higgs boson, researchers at the Large Hadron Collider and other facilities are probing the limits of the Standard Model. They seek to discover new particles or symmetries that could explain the nature of dark matter, the imbalance between matter and antimatter, and other unresolved questions. These high-energy experiments, involving collisions at unprecedented energies, are as much an exploration of human ingenuity as they are of the universe itself. Each data point, each anomalous signal, provides a potential clue to the underlying structure of matter, pushing theoretical and experimental physics forward in tandem. The exploration of the cosmos on a grand scale complements these microscopic investigations. Telescopes and space observatories are capturing phenomena billions of light years away, probing the origins, composition, and ultimate fate of the universe. Observations of distant supernovae revealed the accelerating expansion of the cosmos, leading to the concept of dark energy. Measurements of the cosmic microwave background provide a snapshot of the universe just 380,000 years after the Big Bang, allowing cosmologists to reconstruct its early history and test theories of cosmic inflation. These achievements illustrate a profound truth. The universe, in all its vastness, obeys underlying principles that humans can discover and quantify, even when those principles defy intuition. Physics also increasingly intersects with other scientific disciplines, creating hybrid fields that tackle complex, real-world problems. Biophysics, for instance, applies physical principles to understand biological systems, from the folding of proteins to the mechanics of the human brain. Condensed matter physics informs the design of new materials with applications in medicine, electronics, and energy storage. Astroparticle physics investigates the cosmic origins of fundamental particles, linking the behavior of the microscopic with phenomena on galactic and intergalactic scales. These interdisciplinary approaches highlight a fundamental theme in the history of physics. Understanding one aspect of nature often requires integrating knowledge from multiple perspectives, revealing the universe as a profoundly interconnected system. Philosophically, modern physics continues to challenge our deepest intuitions about reality. Relativity and quantum mechanics reveal that space, time, matter, and energy behave in ways that are counterintuitive yet mathematically precise. Concepts such as time dilation, wave, particle duality, quantum entanglement, and probabilistic outcomes force us to reconsider the very notion of causality and determinism. Physics no longer merely describes motion and forces. It describes the fabric of reality itself, suggesting that the universe is far stranger, more intricate, and more interconnected than everyday experience would suggest. These revelations are not merely academic. They reshape our worldview, our understanding of reality, and even our philosophical notions of knowledge, observation, and truth. As we look ahead, the questions that define the frontier of physics are as profound as they are challenging. What is the true nature of dark matter and dark energy? Can quantum mechanics and general relativity be unified into a single framework? Are there extra dimensions or parallel universes beyond our perception? What are the limits of computation, measurement, and observation? Each of these questions represents both a challenge and an opportunity, inviting the next generation of scientists to think creatively, experiment rigorously, and push the boundaries of what is known. The history of physics teaches us that progress is rarely linear. Breakthroughs often emerge from unexpected observations, overlooked anomalies, or bold conceptual leaps that overturn previous assumptions. The ongoing story of physics is also a testament to the collaborative nature of human inquiry. From the early observations of ancient civilizations to the global research collaborations of today, progress is built on the cumulative efforts of countless individuals working across generations and continents. The discoveries of Copernicus, Galileo, Newton, Maxwell, Einstein, Bohr, Planck, and countless others are connected not merely by ideas, but by a shared commitment to questioning, observing, and understanding the natural world. Modern science, with its multinational experiments, collaborative simulations, and shared data, reflects this enduring legacy, demonstrating that knowledge is a collective enterprise as much as it is an individual achievement. Physics, in essence, represents humanity's quest to decode the universe, to find order in complexity, and to understand phenomena that range from the subatomic to the cosmological. Its history shows that curiosity, creativity, and rigorous methodology are the keys to discovery. From the first observations of falling objects and planetary motion to the detection of gravitational waves and quantum entanglement, humans have systematically unraveled nature's secrets. Each discovery builds upon the last, creating a rich tapestry of understanding that illuminates not only the mechanics of the universe, but also the intellectual capacities of the human mind. Finally, the history of physics demonstrates a profound continuity between past and present. While tools, instruments, and computational capabilities have advanced enormously, the fundamental questions remain surprisingly consistent. What is matter? What are the forces that govern it? How does the universe evolve over time? How do the very small and the very large relate? Each era of discovery answers some of these questions while generating new ones, reflecting the iterative, dynamic nature of science. The journey from simple observation to advanced theoretical frameworks exemplifies the power of human curiosity and ingenuity, showing that even the most complex, abstract, and counterintuitive aspects of reality can, over time, be explored and understood.